All right, so we're going to look at solving linear equations in one variable. And the example that we're going to do involves fractions, which is where students usually struggle. But we're going to start out with some general overview of terminology and the procedures generally, and then we'll go through and we'll do our example. So one thing to keep in mind is the difference between an algebraic expression and an algebraic equation. An algebraic expression is an algebraic statement that involves numbers and variables but has no equal sign. Algebraic expressions can be simplified, but they can't be solved. Once we actually introduce the concept of an algebraic equation, students often get these two kinds of things confused. And I've many students, even my calculus students, will still kind of try to force an equation, an equality in there, an equation, an equal sign. They'll just add it someplace, set the whole thing equal to 0 or whatever. Sort of, even though you can't really just stuff one of those things into an expression. They get so used to solving that they don't know when to stop. But an expression can't be solved. You can simplify it, you can reduce it to lowest terms, you can combine like terms, but you can't solve it. You don't get x equals something. You just get an expression that is easier to look at than it was before. An algebraic equation, on the other hand, is a statement with an equal sign. Typically, there's something on both sides of the equal sign, and they're equivalent to each other. And you can manipulate them both by simplification processes that we use in an algebraic expression, but also some techniques that are specific to equations to get equivalent equations, equivalent statements that have the same solution. And the idea is to get it as simple as possible, where you get x equals something if possible. A linear equation in one variable is defined as essentially any statement that is equivalent to ax plus b equals c, where a, b, and c are real numbers, and x is the only variable in the equation. And specifically, a is not equal to 0, because otherwise it's not linear. Linear equations have no powers of the variable, nor does it do anything more exotic, like taking square roots or dividing by the variable or anything else. You can multiply by constants, you can add constants, but that's it. A solution of an equation is a replacement for the variable that makes the statement true. Sometimes equations are sometimes referred to as conditional statements because they don't necessarily work all the time. They only work for particular conditional values for the variable. A solution set is a set of all possible solutions to an equation. This also applies to an inequality, but we're not addressing inequalities in this discussion. And then to solve an equation, again, is a procedure where we write a series of equivalent equations until we get x is equal to something. Now, the steps that we're allowed to use in algebra that we cannot use when we're when we're simplifying expressions have to do with properties of equality. And so these properties are essentially algebraic truths, algebraic statements, algebraic things that we are allowed to do to manipulate an equation in order to simplify it down to x equals a number. Now, we do have general simplifying strategies, as I mentioned before, properties of real numbers, distributive property, combining like terms, finding common denominators, things like that. But these properties of equality are, again, algebraic principles that we can use in order to simplify an expression. So if we have real numbers a, b, and c, this is the addition property of equality. Then if a is equal to b, then I can take a statement a plus a third number and b plus that same third number, and then this will still be true. And because addition and subtraction are essentially the same thing, just with positive or negative numbers, this basically means that if I have an equation, a statement, an equality, then I can add or subtract something to both sides of the equation, the same thing to both sides of the equation. And I won't change the equivalency of the two sides. They will both still be equal. And typically this is a strategy we use to combine maybe variable expressions that are on the same side of the equation, or to simplify a constant that's maybe there's constants on both sides and maybe we only want them on one side. So typically this is used to combine things that are on different sides of the equality statement. So here's an example. 28 minus x is equal to 2x plus 7. I'm going to add x to both sides of the equation. And then negative x plus x gives me 0x, which I don't have to write. And then 2x plus x gives me 3x. And so I've simplified this expression by using this equality property of addition. And then same thing for over here. I want to get x by itself. And so I can add a negative 7 to both sides of the equation. 7 plus negative 7 gives me a 0, so I don't have to write it. And then 28 minus 7 gives me 21. So again, I've used this equality property of addition, this addition property of equality, in order to simplify a statement that had x on both sides and a constant on both sides, so that I just have one term that includes x and one term that is a constant. The multiplication property of equality basically says that if I have an equation statement, I can multiply both sides of the equation by the same value. Or I can divide, as long as I'm not dividing by 0, because multiplication and division, again, are similar properties, similar operations. So here I want to get x by itself, so I'm going to divide by 3, or you can think of this as multiplying by 1/3. That's going to cancel the 3's because 3 divided by 3 is 1. So I get 1x. And then on this side, if I divide 21 by 3, I get 7. So now I actually solved this equation because I have x on one side equal to a number. Now there's one additional property that we sometimes use, but rarely really think very much about. And that is that the symmetric property of equality basically says that if you can say that A is equal to B, then you can also say that B is equal to A. The sequence that you put the variable and the number on which side of the equality doesn't make any difference. And again, this seems kind of obvious, but sometimes it's worth stating it, because there are actually certain situations in which in some kinds of mathematics where this isn't necessarily where we're just switching things around isn't as clean as this. Now, the substitution property is going to allow us to check our answer. And so we've decided that x was 7. And so if we take our original statement and we plug in the 7, then instead of 28 minus x, we have 28 minus 7. We can simplify this to get 21, and then on this other side of the equation, we replace x with 7, which gets us 2 times 7 is 14 plus 7, and 14 plus 7 is 21. And so we verified that if you plug in 7, both sides of the equation are true. Now, steps to solve equations. Generally, the strategy is that if you don't have any fractions, you can kind of jump ahead. But generally, if you're dealing with a problem that involves fractions, which is the example that we're about to do, you generally want to clear any fractions or decimals, particularly fractions, because whole numbers are much easier to work with than is anything involving a fraction. You don't have to simplify involving a fraction if you have an equation. If you have an expression, you're just stuck with the fractions. But if you have an equation, you can make your life easier by getting rid of the fractions, by clearing the fractions, by multiplying by the LCD. So using that multiplication property. And then you're going to try to simplify each side of the equation by removing any grouping symbols and combining like terms. And then you want to group all the variable terms on one side and all the constant terms on the other using that addition property. And then finally, it's a good idea, especially when you're learning this for the first time, to check your answer in a calculator or by the substitution property we talked about above, plugging it in and making sure both sides are equal. If you're going to make mistakes, and particularly when working with fractions, this is very common, you want to check your answer, and you honestly want to check it in the original version of the problem, not after you started manipulating it, because if you make a mistake early, it'll seem like, even if you did all the rest of the steps correctly, like your answer is correct, even though it won't actually work in the original problem. All right, so let's look at our example. So this is our example. This is a kind of complicated example intentionally so that we can see what all of the procedures are. Now we have three fractions. I apologize for the lawnmower in the background. We have three fractions. They have denominators of 6, 2, and 3. The LCD is 6 because 2 times 3 is 6. So they all divide evenly into 6. So what we're going to do is we're going to multiply every term in the expression by 6. So using that multiplication property. Now, first, we're going to multiply every side of the equation by 6. So I've taken this whole side and I've multiplied it by 6. I've taken this whole side and I've multiplied it by 6. Okay, step 1. But then, in order to simplify, I want to distribute that 6 to every term. So this 6 will get multiplied by this thing, which is all one term. And then it will also get multiplied by this thing. So 6 times this thing, 6 times that thing, and this is only one term, so it's just 6 times this one thing. Because 1 minus t and 1 minus 3t are in parentheses and they're multiplying the fraction, it all counts as one term until I distribute. Now here I'm going to start reducing. So 6 divided by 6, that cancels, and I'm left with just 5. 6 divided by 2 cancels partially, and I'm left with just a 3, because 6 divided by 2 is 3. Here, I'm canceling 6 with the 3, and I'm getting a 2. Don't lose this minus sign. Now we're going to simplify by distributing like terms. So notice here what I've done, though, when I get to this stage, there's no more fractions. So much easier to work with when I don't have to deal with fractions. So now I'm going to distribute using the distributive property. I'm going to distribute the 5 to both of these terms. So 5 times 1 is 5. 5 times negative t is negative 5t. The 3t is outside the parentheses, so I don't distribute the 5 there. I just keep it. Negative 2 times 1 is negative 2. Negative 2 times negative 3t is positive 6t. Don't forget that you're distributing that negative sign as well. Now, on this side of the equation, I can combine my like terms. Negative 5 and negative 3 have the same sign, so I add them. I get negative 8t. These two don't have any like terms. There's nothing I can do just yet. Now we're going to try and get the variables together. And we're trying to put them on one side of the equation. So there's no real sort of strategy. You can pick a side. Sometimes I like to make sure that I end up with a positive coefficient for t, just because I don't have to then worry about the minus sign later on. But it really doesn't make any difference in the end. But here I'm going to add 8t to get rid of the negative 8t on this side. But I have to add that 8t to the other side of the equation. Negative 8 and positive 8 cancel. They give me 0, so it goes away. But 6 plus 8 is 14t. So I end up with the 5 still there, the negative 2 still there, and then 14t. And then I do the same thing for the constant. I want to put this constant on the other side of the equation. And I do that by canceling it on this side by adding 2. And if I add it on this side, I've got to add it on this side. 5 plus 2 is 7. Negative 2 and 2 is 0, so I don't have to write it, but I still have 14t. And then I want to get the variable entirely by itself, and I go back to my multiplication property. I divide by 14. Again, I can divide by anything I want as long as it's not 0. If this is already a fraction, use your reciprocal to multiply rather than divide by a fraction. But this is equivalent to multiplying by 1 over 14. 7 over 14 is 1/2. And so what we get is t is 1/2. Now, when you're dealing with a problem that has a lot of fractions in it, checking a fraction result in a problem that has fractions can be difficult, but it is necessary to go all the way back to the original problem, because if you made a mistake someplace, this is where you will find it, is it plugging it into the original problem, not plugging it in sort of part way back, maybe after you've already made that mistake. So we're going to plug it in our original equation. So t becomes 1/2, t becomes 1/2, and t becomes 1/2. Now we're going to simplify a little bit. 1 minus 1/2 is 1/2. 1/2 divided by 2 is 1/4. 3 times 1/2 is 3/2. I'm going to distribute here. 5/2 times 1/2 is 5/12. The 1/4 hasn't changed. Here, I'm going to simplify 1 minus 3/2. 3/2 is 1.5, so this becomes minus 1/2. And then I'm going to add these terms with I have to find a common denominator. The common denominator is going to be 12. This will become 3/12. So 5 minus 3 will be 2/12, which reduces to 1/6. And on this side, the negative and the negative become positive, and 1 times 1 is 1, and 3 times 2 is 6. I get 1/6, and 2/12 is equal to 1/6. So we know that both sides of the equation are in fact equal to each other, and this is the correct solution. Again, plugging in fractions can be challenging, but particularly until you're sure of your mathematical skills, you should check every single time in the original equation, not in some sort of intermediate stage.